Okay, before we do the binomial expansion, we need to understand the rationale for doing binomial expansion first. Alright, so first thing, what this table actually let us see is in any quadratic expansion where you have 1 plus b to the power n can be in the form of any integers which are positive. So they take the different form. N can be equal to 0, 1, 2, 3, all the way to the power 4. If I were to do the expansion very meticulously, you can do the expansion. But this is only up to power 4. But we want to see certain pattern. You may not be able to see yet. But the thing is, if now I want you to expand power 20, it's unlikely we're going to do this method. Because if I need to do this method means I need to do 20 times. By the time I do until 20 times, half an hour is over already. So there ought to be a shorter method. How do we do the shorter method? Before we do that, we need to discover something first. Based on this table that you have, we're going to go down to the page below. Alright, so based on whatever coefficient was given in the expansion earlier on, now I'm just going to get the responses. So just fun, for n equal 3 will be 1, 1, 3, 1, 3, 3, 1. Okay, let me write down. Nosham, n equal 4, 1, 4, 6, 4, 1. Am I right? Okay, I need to enlarge a little bit. Do you see any pattern over here? What about the 1, 2, 3, 4? So how do we get the numbers? Do you see any pattern? Yes, the two numbers on top would add up to the next number below. Alright? What do I mean? Let me draw the arrow. The 1 and 1 will give you the 2 here. Am I right? You notice the side are always 1. But to get to the next term, 1 plus 2 will give you 3. Likewise, 2 plus 1 will give you 3. You all see the pattern now? Likewise, the next one. 1 plus 3, 3 plus 3, 3 plus 1. But the one at the side will always be 1. Okay? Based on this new discovery, can you help me with n equal 5 and n equal 6 right now? Okay, Jin Hao, can you share with us? So for your row for n equal to 5, what will be the final numbers that will come out? 1, 5, 10, 10, 5, followed by a 1. Alright? Which one? How about for n is equal to 6? 1, 6, 15, 20, 15, 6, followed by a 1. Okay, whatever you see right now is known as the Pascal's triangle. Alright, your textbook at the top also mentioned this is known as the Pascal's triangle. So we are actually making use of the Pascal's triangle for this topic in binomial theorem. But teacher, n is equal to 20. Am I going to do the Pascal's triangle until like that? Cannot be one. Or it will be too tedious already. And I don't need you to memorize. Of course, we can make use of the calculator. But wait, hold on first. Okay? Let's do some observation. Then I'll teach you how to use the formula as well as the calculator. First thing and foremost, let's go back to this again. When n is equal to 1, when n is equal to 0, when you expand, right, 1 plus b to the power 0, how many terms do you see? 1. There's only one term. When n is equal to 1, how many terms do you see? 2. When n is equal to 2, how many terms do you see? 3. Sorry. Oh, very boring. Let's make a guess. When n is equal to 20, how many terms do you think there will be? Very good. So if n is equal to 100, how many terms will there be? 101. But don't worry, if I give you n to the power 100, I will not ask you to expand 101 terms. Later you see in the question, they only need certain terms. And those certain terms, you can make use of the calculator. Can? Alright, that will be the introduction to binomial. Alright, it's actually making use of the concept of Pascal triangle, but I will teach you how to use the calculator in the short while.